My name is Vladan Djakovic. I'm with iDevices. It's a company that makes everything from things, apps around them, and infrastructure to connect these things. Before joining iDevices about 3 years ago, I was doing different kind of infrastructures, from silicon to game distribution, high-performance computing, P2P cameras for consumers. So I was kind of always where lots of servers are, and there is a lot of infrastructure to be done. This was very interesting because this was an opportunity for me to do something really exciting and very, very interesting. The opportunity was that this could have been done from scratch, and I'll explain why we did it from scratch and how it went. So, essentially, I'll be talking about what is this high-performance switching fabric for IoT, what problems we encountered, and what did we do about that. So what is Internet of Things? It's really millions of devices, small computers on most of the time, and they sit and they wait for something to happen. It happens very rarely. They send messages out about environmental things, temperature, humidity, and so on. These things talk to backend servers, and they talk to handsets. That's what they do. And what we really do, our infrastructure is making this connection between handsets and things and backend servers work. As you know, everything is behind net these days. IPv6 never happened. So this infrastructure is really taking care of things that should have been taken care of by IPv6, and they're not being taken care of that. So it's a custom backend. The main goal, the main rationale was to cut down the cost. Today, if you want to, you have a thing and you want to connect it, and somebody is going to run backend for you, even though your local commercial services for that is going to cost you between $1.50 and $4.50 or $5 per device here. So if your landed cost of the device is $20 and you're making $10 profit, you're selling to 30, the question comes, who's going to pay another $10, $15 for the lifetime of the device? And this is totally an unanswered question. I mean, this sounds so obvious, but this is totally unanswered question. When you have 20, 30, 50 devices per human, people are not going to sign up for 50 accounts. There is not enough data coming from this to be monetized to keep up with these costs. It just doesn't exist. So the things have to become as simple as plugging in the wall, electricity, putting a plug in the wall outlet. If you had to have a relationship with your PG&E for everything you want to plug in, electricity would cost like 100 times more. Oh, I'm going to plug in my hairdryer, I'm plugging this, how are you today, you want to buy something, and so on, right? So that's a non-starter. These things are not handsets, they're not computers. There is no money in eyeballs there. So the costs have to go down, and the goal here is to cut it down by essentially a couple orders of magnitude, which we did. Also this whole infrastructure is pretty much invisible. The devices are primed and enabled during manufacturing. There is nothing for user to do to connect. Of course, the application on top can do whatever they want, but for basic connectivity, there are no user interactions. There's no onboarding. There's no onboarding. It's a zero onboarding thing. And to get this cost down hundreds of times, we had to cut down on electricity, cut down on the server requirements, and cut down bandwidth. So this is how we did it. We went to all UDP-based protocols. We call it IoT IP. The name held for a couple of years. It's fully distributed server mesh. They join the thing by themselves, the system by themselves. There is no control panel. There is nothing. Basically, you cannot even log into the service. They are appliances, and they are made to join the existing system or existing systems. And once they join, there is nothing you can do to them. I mean, there is absolutely no command and control center, nothing like that. The mesh is fully distributed, so you can just keep adding servers. And the only interaction you have with the server is when you provision it. There are no other interaction with the service whatsoever. It's very efficient. Because we run into bare metal, we pay per CPU cycle far less than we would have when we go to rental services. They rent VMs. UDP is far more efficient than TCP. The requirements are relaxed. It's not important you get every message. You get most of them. The baseline UDP loss is around 0.4%, so it pretty works well, and you spend a couple of times less on bandwidth for that. We buy our bandwidth directly from tier 1 backbone providers, so we pay many, many times less than you would pay when you go to service providers like Amazon and others. So to give you an idea what we're doing, we are essentially executing close to 100,000 sessions per second per pizza box, and we can host about 1 million concurrent clients on that. If you compare it to others, you'll see it's far beyond anybody else is doing, as far as I'm aware. It's secure, so there is a client-to-server encryption. There is end-to-end encryption in SDK. They both have forward secrecy. The servers do not understand the namespace of clients, so they don't know who they are, so there is nothing server can snitch on anybody there. And servers generally don't understand data the clients do. So there are no honeypots. That's the point. That's very important to have security. So what happens on each of these pizza boxes? There are hundreds of UDP sockets on multiple interfaces. We always have multiple backbone providers terminating in our cabinets. Each packet has predictable load, which allows us essentially to shape load on the network interface. All traffic is encrypted. All crypto is in CNIFs. I would say that 50, 60, 70% of our CPU is cryptography. The message switching service dispatches the packet out in less than a millisecond, and we have ephemeral storage service, which is mapped to RAM and disks, and we have our custom C-thread pool, and we have to write our custom database for this. When we deploy nodes, you bring the box, you provision from bare metal, and then it's done. There is no repair. If something breaks, it breaks. There's no software repair. The software just runs. Basically, you cannot log in these boxes. The typical test cycle for node distribution is a couple of months because they have to run for a long time. And the typical lifetime of release is between 7 months and almost a year. So we have beams running like for a year continuously. And again, remember that our users are machines. They're up 24/7. The load is pretty much uniform, and sometimes you get surprises, which I'm going to talk about. So these things are actually less forgiving than humans. We have to support forever all the devices ever deployed, even early on when we didn't have all the things right. So we have ability to handle multiple protocols, because once you sell something, you have to support it forever. If you drop support, it's really bad for business. The load matters a lot, because we are extracting the maximum out of each kilowatt and each space and each bit. The load is quite high, the stress load is quite high on the servers, so it's very hard to replicate that on test beds. Whenever you slow it down, it behaves differently. It's not the same thing. That's one big problem we had, that how do we test this as a high load? The input traffic is impossible to replicate. It's a couple of gigabits per second per cabinet. And UDP is different from TCP. You are going to see things that you didn't even know existed on the internet. So we tried to do, of course, we came traditional way. We tried to do logging. If you log things, our servers slow down like 10 times. So the scenery changes and you don't have the problems you had before you started logging. Even if you just send messages to a single process and not write that on the disk, it slows down a couple of times. I just want to make sure the version here and mention Erlang and why we're using Erlang. There was nothing else that could do this except Erlang. IoT is mostly one-to-one communication, but you have millions of them. They're not connected to each other, right? So Erlang, this microthreads that Erlang have is just made for this thing. There's nothing else that can do it at this capacity-based load. That's why we went for Erlang. However, again, the problem is how you do debug this system. We cannot replay the traffic. It's unpredictable. It's just too much of it. So basically, we have to go back to the basic code walkthrough here. Something goes wrong, you sit there, and you spend hours looking at the code and trying to figure out what happened. To help people do this, we had to figure out how to narrow down the problem space. And this is what this talk is about. So we need to visualize the system. When we look at things, it's always the whole system of huge number of devices. We never look at individual threads because that's impossible. The devices are unpredictable. They talk simple things. And actually all these things that happen between one device and its peer have been debugged during development. That's not the problem. The problem is what to do at a high load. So the picture had to include everything, from performance of servers, performance of backbone pipes, and group performance of clients. If you have problem SDK, a group of clients are going to exhibit different behaviors. And all this had to be done without hurting performance. So we designed this thing that we call Pulse. It's a custom instrumency system. It uses our own UDP-based protocol that we use for other clients for real-time communication. It has a subscription model. So essentially, the aggregation runs on infrastructure nodes themselves, but the actual subscribers are outside, usually put them on EC2. It's secure because we didn't have any additional ports. We didn't have to open anything else. It uses the same security as our basic protocol. And by the way, we have our protocols audited, and we do it regularly. We pay a lot of attention to security. It collects data from multiple sources. Some data is collected from the beam itself, and I'll talk a bit about that. And the other stuff is collected from the operating system. This is not business analytics. This tells you nothing tells you a bit about clients, but this is really not IoT analytics as it's mostly understood today. You know, what clients do, how many times they switch on, whatever they switch on or off, and so on. This is about system performance. So again, it's a subscription model. Subscribers run usually on Amazon, on EC2 or multiple zones. Subscribers decide which nodes they want to monitor and what they want to monitor on each node. The publisher is a daemon on node, and it pushes data to subscribers, and typical rate is essentially 1 packet per second per metric. So it's very, very, very low bandwidth. On the node, publisher is separate daemon. We wrote it in C. The communication to the rest of the system is through Unix domain sockets. The publisher binds to it, so if it dies, that's fine. Others just can't write to the socket. They just skip that packet. The data comes from the beam, and we have dependent daemons that collect OS statistics such as CPU usage, disk performance, network performance, and so on. So the important thing is to understand is the publisher and has no effect on system performance. It can die, it can go away, it can have problems. It does not affect the network performance. The processes in the beam that send data to publisher are very lightweight. They collect some counters and so on. There is pretty much nothing per client. These are aggregate things, and they essentially wake up every second and send the number down the Unix domain socket. So what do we collect? From the beam itself, some of the data we get, a number of clients, number of concurrent sessions. From the OS, what is the beam's current memory, beam CPU, which is going to be very important actually. How many packets per service we have in and out, what storage system doing. And we're also polling the node from the external subscriber himself to get the sense of efficiency, as we have standard battery tests, and we measure the latency. And the subscribers where we present data, there are separate instances. We run them in situ. We are currently using Graphite as a database and Grafana as a rendering engine. We keep a lot of history. The history is very important because sometimes you're going to realize that there are things that you should have paid attention to and didn't, and you go back a month or two and say, aha, this is what happened then. So it's very important to keep a lot of history. If you're not familiar with Grafana, you will see some screenshots. It's a web interface for display. You can configure it in different ways, and users, which are basically system people in-house, they have to learn how to use Grafana to see different stuff. The system is made such that we can interface it to other display engines, and we actually consider some commercial display engines. Hopefully, they're going to be, I mean, if we find them more useful than Grafana. So I'm going to show you a couple of examples. And important thing to understand here is that because we had to develop this from scratch, we didn't really know what to look for. And again, going back to the whole project, when we started, nobody knew Erlang. I mean, so it's not like anybody was experienced Erlang programmer or whatever. Erlang was just the only tool that could do the job. So we had to learn as we move on. And the important thing we understood is that you have to display as much as you can. You don't know what you're looking for. You want original data, non-derivatives, and you're going to get surprised how good our eyes are, how good the visual system is in humans, that you're going to spot things which you never thought you can spot, but you have to give it some data to work on. So let's start from very basic stuff. This is observing the beam memory in normal operation. So when you boot a machine, you're going to see how over a couple of weeks the beam memory goes up and then stabilizes at some point. Essentially about once a day it does small jumps and then it stays there, and then when it gets to some maximum it hangs on there. And if you blow up this maximum, you're going to also see, so the bottom one is the week worth of observation. You see that about it does garbage collection approximately on daily cycles. We never went deep into the garbage collectors to figure out what's really going on. We tried a couple different ones. But once you see this and say this is normal, then you can spot the abnormal stuff. And to give you some ideas, our machines have usually 100 gigabytes of memory. So this is, there's quite a lot there. So then this is one example what to look for when you do debugging. So there's a problem and the node goes down, which happens very rarely. So actually we had the node go down not due to hardware failure in once. So it's like once in maybe, tens of several years. So we were essentially looking for straws, and in this particular case, we have some testing was going on with the third-party gateway, and we isolated that traffic there. And what we did not notice is that node went down after one of these tests, right? So this gives you just an example that you don't know what you're looking for, but you have to go to a bunch of these diagrams and graphs and then try to make inferences what could be the reason that things went bad. Again, this is observing the normal situation, and this is how we track that when a node fails, that clients are redistributed on other nodes. In this particular case, the graphs are stacked and they show number of clients per machine. This case, it was a 4-machine setup. And one went down. It was actually a disk, the storage failure. So when it falls down, when it goes down, the clients, so you can see here that number of clients went to 0, basically, right, from some number there. And then you can see the clients on the other machines within basically a minute and a half, the clients from this machine migrate to the available machines. So when something like happens, you look at this and you say, okay, it worked well, so everything's okay there. When things are not okay, you're going to see these things longer, or you're going to have clients having problems migrating and so on. Again, you're watching here a huge number of clients. It's not one client or anything. This is group behavior. Then you see things that you didn't think you were going to see. In this particular case, we are observing at all times essentially the latency for the standard battery of tests that we run against our service. And we have a bunch of these test machines, and there are different coasts, and as we have servers on both coasts. What is normal situation is that these tests are essentially 99% of the latency is the travel time. So this is pretty monotonous curves, and you can see here that this one is from the same coast where the actual test server was, and this one was the opposite coast. So you have difference in travel time, speed of internet, not speed of light. And what happened is that we just saw that the near coast thing went all the way up, and we had no clue what's going on. I mean, it was totally, we didn't know what was going on. So then we isolated the backbone provider that was involved in this, and we started to do trace routes. So what happened is, as we found out, that the fiber was cut between, I think it was between Seattle and Bay Area, and they had to reroute. They rerouted through Kansas City. So we were quite surprised when we saw our packets are going through Kansas City between these two machines, but that was the cause. And actually the provider didn't think we were going to notice, so they apologized later on. And I think from now on they are going to tell us ahead of time when things like this happen. One of the things that we do regularly is do stress tests, where we basically load servers to capacity, where we expect some packet loss, which is how we deal with overload. And here you see a basic trace from a couple of those stress tests. You have down there is CPU, which you never want to hit saturation, so it's kind of close to 100% there. And you see input and output packet for a particular service, and you can see how in normal operation the packets are kind of the same number in and out, but when you do stress test, there's discrepancy there because there's packet loss. This is not very accurate, but this really confirms what our stress harness is telling us, so this is kind of sanity check when you look at these things. And then there are client bugs. Clients, of course, all clients that we have, we deliver SDK, and SDK essentially is presenting kind of coherent interface to our protocols. And the basic expectation is in the protocols most of the time is that a number of input and output packets should be pretty much in sync unless there is overload. So here we observed something interesting. This is not overall situation. This is blow up of particular place in the curve that we saw that there are more input packets than output packets. And these clients had some problems, so this was one indication that you can, although you're seeing group behavior, many clients, you can still make inferences that there is something wrong with the SDK out there. This is kind of business data that actually the company really like to see. This is a number of clients over a couple of weeks. So although this is system testing, this is actually tracking the sales. So you can see how the clients are going up. And the glitches are glitches with pulse. So they're not going up and down every day, but we have some problems instrumenting there. That's one thing you have to keep in mind, that your instrumenting system also has problems. So you should always take whatever it tells you with a grain of salt. And there are things we don't know what they are. So for example, what we're observing, sometimes we have this increase in beam memory and CPU usage, and we have no idea what's going on. Absolutely no idea what's going on. It doesn't seem to be a problem. But it's kind of disturbing that there's something going on that you don't know. So we're keeping an eye on that, and we get some bandwidth. Somebody's going to go and try to figure out what is this about. So that's pretty much it. Again, this is dealing with high number of clients. You want to be very fast and very cheap in your operation, very low cost. You always see the large group, and you want to kind of make inferences what this large group is doing. When you start, you don't know what you're looking for, so you need to display a lot of things, and then try to figure out what's normal, what's not normal, and trust your eyes that you are going to see the difference. Sometimes you can automate. So if you see things going wrong in a specific way, you can, of course, automate that and create alerts. So you don't have to count on your eyes anymore because you have observed particular patterns and you have automated them later on. The instrumenting system is always going to have bugs, so you have to be ready for that. Sometimes, we get excited all for nothing. It was not a problem. It was instrumenting thing. And in IoT, SDK is what determines pretty much everything. So this is not web browsing where you have browsers and well-defined protocols, whatever. Everything uses SDK to connect to this. And one thing that we do is that we use the system to evaluate the new SDKs as we do new releases to make sure that there are no differences or there are no new problems introduced with that. So that's pretty much it. Any questions? Go ahead.
You mentioned early on the security of basically the servers talking to all these things out of the Internet of Things. And you mentioned they were, if I heard you right, they were mutually authenticated. In other words, both sides got to trust the other side. But you said it was all just, plug and play and just start it up. How do you do that?
The devices, the actual firmware clients, hardware clients, they are primed in the factory, and we give them a beer certificate, which we call a coin. We sell it to them, right? So that coin has certain performance characteristics. You can do so many packets, so you can do like 10 packets a day, or you can do video streaming, right? The coin is going to be different, of course, it will cost different. And that coin is all that our system is asking for the client.
Okay.
So it's
installed certificate that the
correct.
Cloud server already knows about.
Yes, yeah, and it's installed in manufacturing. It becomes essential part of bill of materials. Okay. So you don't have to think about that. It is there and it's going to work, and usually it's lifetime of the device.
Okay. Thank you.
Yeah, go ahead.
For the UDP server, what's the architecture? Are you using like SO reuse port, or?
I'm sorry?
For handling large amounts of UDP traffic
Mm-hmm.
on the server, how are you scaling? Because you can only do one listen on one socket typically.
Okay.
Are you using SO reuse port on Linux? Or?
No, so our servers are FreeBSD. We use FreeBSD. We have a couple of gigabit Ether interfaces per box that go to different bandwidth providers. So we use FIPS, different routing tables for different providers. And inside each service, and we have like 3 services at this time, 3 kinds of services. Each service has a wide range of ports, which are randomly chosen by clients. And on each of these ports, there's a process whose only job is to get a packet and figure out who to send it to inside. So per client processes are they're doing the encryption, and the rest stuff are that they come up as clients come up and go away. But the processes that actually triage traffic from the port, they're one per port, and they're very fast because they just get the packet and figure out do they need a new process to process that packet, or is the existing one? And that's essentially done on the source basis, so it's very fast. So we have about, per server, we have, say, 500 ports. So that helps. Yeah, go ahead. You have a question?
Yeah. So can you elaborate on that dispatcher? Sorry, I think you said you had a dispatcher down on the NIC, is that correct?
We have a dispatcher per input socket. So on FreeBSD is really good on networking. It's very stable. So again, we have hundreds of ports open, which are basically randomly chosen by clients. So we have a client side, if you will, load balancing. And when the packet comes, there is one process per port. So many processes per interface that is just looks at the packet and decides based on the original packet who to send it to. It does not decrypt, does none of that. It just sends it to the process that is going to handle that.
When you say process, you're talking about an Erlang process?
This is all Erlang processes. This is all Erlang. I mean, the dispatchers, it's all in Erlang, yes.
So even from the dispatcher or from the UDP interface, your first dispatcher is an Erlang process?
Erlang opens the sockets, yes.
Right.
Erlang opens the sockets, yeah. Erlang opens the sockets.
I already asked this.
Oh, go ahead.
What, if anything, of this is open source code that you put out? What is code of others that you're using, and what is all just proprietary that's only good inside?
So we operate our own servers, and we use Erlang, OTP, and FreeBSD. On the server side, it's pretty much all our code. There is nothing else. Yeah.
On the guessing you have requirements for your clients about the outbound networking for instance, how your UDP packets traverse the local networks. Do you provide those requirements?
So it's pretty straightforward. The protocol itself has a poll mechanism. So the clients essentially send the heartbeat packets every couple of minutes. If we find out that the net window is less than that, which sometimes it is, then we calibrate that and they say send packets more often, which means that we keep the net open with very low overhead traffic. And so the clients can receive traffic at any time because we do keep the net open.
Do you do like white? Oh, I'm sorry.
I'm sorry. Go ahead.
Just for clients that are different types of requirements, do you offer white labeling of the traffic outbound so that, for instance, the network destination from the embedding into the device, right? Or is it always your proprietary networking? Talking about the call home addressing.
Okay, so you mean what is the target? Where do clients send packets, right? The load balancing is on client side. So clients have a service directory, and they calculate which one to use. And we have the thing we call words. So we can limit the clients to a particular geography if that's important.
But you're doing all that over DNS, presumably, right?
We never use any DNS. No, DNS is totally out of picture. DNS is, we don't have any fingers in our protocol.
Okay, so part of the SDK you provide to the guys.
Correct, yes.
Well-known IP address.
Correct. So what happens actually inside is that servers maintain by their own a service directory, and they kind of have consensus on that. And there is a thing we call directory service, right? And each server has that. And then clients, when they're born, they know a couple of known names, and they learn more as they move on. So basically, once a day or so on, they pick up a new listing for clients. And the listings are long persistent. So the machine goes down, it's usually up within 24 hours. That doesn't affect service directory at all. The service directory main thing is when you add servers. That's the most traumatic thing, right? And the clients have to find a new server to go out there.
So do the clients gradually migrate some
Correct. Yes.
proximity to geography?
It depends. It depends. So there is a thing that we call world, and they overlap between data centers and servers. So essentially, when you add the new server, which wasn't there before, clients will eventually redistribute to use the new one. Yes. Oh, go ahead. Sorry.
For the hiccups that you have no idea what they are, what tools have you tried to inspect the
I don't have a good answer to that. So the things that do not bother the service, we put on a back burner. And we kind of aware that they're happening, we don't care. These hiccups that I show you, the bumps, they're kind of, CPU goes up, you know, not much, but you can see that, right? So we didn't do anything so far. We just didn't do anything so far, we just kind of keep an eye on that. And it's been going for a while, it could be totally benign, so we don't really spend time on things which don't affect the service.
Dtrace might be, since you're running FreeBSD, Dtrace might be the tool of choice here.
Yes, but what is the CPU impact of that?
Should be low, but it depends on which trace.
That's, I mean, Dtrace has been designed to not interfere with the
Yeah.
environment, so.
But you could also introspect the VM with like something like NDOP or something, just looking inside the VM. It might just be message queues that are queued up and it's doing more processing with the user.
Yes, yes, we could.
And slowing down and the memory increases.
So just compare one thing. These are appliances, so they're not demons. They don't listen to anything.
Right.
So, I mean, the question is how you get there in the first place to do that. So we have really good stability. Again, these things run for almost a year. So we keep a list of things that are potential problems, but you know, you have to prioritize and see what you're going to solve first and what you're going to solve next. Anything else? Yeah.
More general question, since from an SDK perspective, what capabilities do you provide to the devices other than
Okay.
describe what, and
So-
related to that, what's the addressing scheme?
Sure. So there is a talk on YouTube. If you look my name, you're going to see the talk about that, which I gave at developer conference last year. And very in a short is we provide two basic services other than directory service. We provide conduit, which is real-time communication. You pick your address, it's 128-bit thing, so it's like a pin, we don't know what it is, and you talk to the other guy that happens to know the same thing, right? And within conduit, we have a datagram mode, obviously, and we have reliable mode as well. So you can send messages, there are retries, and so on and so on. We use conduit for our own devices to piggyback other protocols on that. So we piggybacking other protocols which expect you know, TCP/IP or so on. We can piggyback them on this protocol and provide more connectivity. And the other service we provide is ephemeral storage. It's either short-term, 4 hours, and then it just disappears. It's all also datagram based, so every record no more than 1,300 bytes. It has 128-bit key space, and we have a long-term, which is 7 days. And what you use this for, if you client-based logging. It's great for video broadcast because one guy writes and many of them can read, and you don't have to bother this guy here. So those are the two basic services we provide. So they're both kind of communication, just one is kind of delayed, can be delayed for a week, and it stays, hangs on there before it's been picked up. And so far, because we have many different classes of devices, we didn't find need for any other service really. This real-time and this delayed communication pretty much covers everything.
That's about it. It's lunchtime, and I don't want to, we're so close to the lunchroom here, I don't want any of you guys to be stuck out there. We have a round of applause, please.